going to send this over to Ken, and he's doing this in hip waders today, but I think he'll be okay. Ken, you there?
I'm here. And thank you for asking me to provide this webinar training. And maybe I need to explain a little bit about the hip waders. If anyone hasn't been paying any attention to the news lately, we've got some major flooding issues going on in North Dakota. We have a river that has come through Minot, North Dakota, and has inundated about 4,500 homes there, and they're continuing a major battle. Plus, the Missouri River is running at beyond capacity, the most flow that has been going through the river, they claim, and we've got about 1,000 homes that are fighting water along the Missouri, particularly in the Bismarck-Mandan area. And then if that wasn't enough, we've got some lakes here that continue to expand and take over farmland and create extremely high water tables that give us continuing water issues. So that's the reference to the flooding and the hip waders. But today we're going to talk about energy efficiency in grain drying, and it has become a very popular topic. And I think part of the reason for that is that is if you read the intro, there's a large energy requirement associated particularly with drying corn, and there's a potential for a large energy savings if we can do it more efficiently. And so I field a number of calls from farmers who are comparing grain dryers, looking to purchase an energy efficient dryer, improve their energy efficiency, and reduce their operating costs. And so that's really what the focus of today's presentation will be. And I've got a number of slides prepared that will cover some of the key energy efficiency features or issues that we look at with various types of grain dryers. And then we'll try to have time also for a question and answer session. So with that, we'll go ahead and move to our next slide. And if you look at the literature, I guess I'm old enough that I went through some of this in the 70s and 80s as well. And, you know, at that time there was a fair amount of focus placed on do not dry the grain if you don't have to. You know, let it dry some in the field. And it's going to vary depending on what state you're in as to just how long we should leave it dry in the field and at what point are our field losses or harvest losses going to exceed any savings that we're going to gain. So these numbers will vary a little bit from state to state, but studies have been done to try to identify at what point are we economically beneficial leaving it in the field, and then at what point do we really start harvesting and doing the drying in some type of a dryer. And most of the literature will talk about somewhere in October is roughly where we make that transition. And there's a couple of things that a person needs to look at. Certainly weather uncertainty is an issue, but trying to estimate what the field dry down rate will be is an important piece of that. So here in North Dakota, what I did was to look at various months during the year, starting September and running through May, look at, based on the average weather conditions outdoors, what we would expect the final moisture content of that corn to be, and that's the equilibrium moisture content listed there. So in September we would expect it to dry down to about 15%, October 16, November we're up to 19, and December at 20%. So once we get to the point of what I call the winter months, the potential for achieving a low enough moisture content that we're gaining by leaving the corn in the field is greatly reduced. Some of the agronomists have looked at growing degree days as a way to try to estimate the amount of field drying that will occur. And so that's what the next column is growing degree days. And I really don't see a very good correlation between growing degree days and field drying. But when we looked at what are the various parameters that affect dry down in the field, it's the same kinds of things that would affect the moisture required for a crop to be growing in the summertime. And so looked at some of the work that was done with calculating potential evapotranspiration. So the next column there is the inches of potential evapotranspiration occurring for the various months during the year. And of course that's in inches of water. And then the next area is looking at translating that to the potential for drying that corn in the field. And you find a very good correlation between the PET, or potential evapotranspiration, and the amount of field drying that is occurring. And as we would expect, in September, we're looking at good drying conditions. October is still good drying conditions, but as we shift to the winter months with the cooler temperatures, higher humidities, the amount of drying potential that is there really drops off. And so this has been useful in two ways. One, it helps us, again, to make a decision as to how long do I leave it dry in the field and make use of that energy efficiency, and at what point do we decide that it's really time to harvest that corn and move it into a high temperature dryer or some other type of drying system. And I think that typically, again, just like the work has shown, that sometime in October is when we really need to be thinking of making that change and going to high temperature drying or other forms of mechanical drying. We had a few years where we didn't harvest the corn over winter because it was too wet, and so we also looked at the potential for drying in the spring, and that's why those months are included on the table as well. As we start looking at the types of drying that is available to us, natural air, or some people refer to it as ambient air drying, is probably going to be the most energy efficient drying system. But I've put in red letters at the bottom of our slide here that is if properly designed and managed. And I have found a number of cases where either it isn't properly sized, the equipment has fans that are too large, heaters that are too large, or it isn't managed appropriately, and then we end up being a very expensive and energy inefficient drying system. And one of the things that as we look at outdoor environmental conditions, we find is that natural air drying requires warmer temperatures. So as we get into the cooler winter months, it just is not very energy efficient or effective at drying grain during the winter. So the natural air drying definitely has an application for us, but it comes with some limitations as well. One of the things that I've found farmers to do over the years is to want to add supplemental heat to grain dryers. And this first table is going to look at natural air drying wheat, and I'm not sure how much natural air drying of wheat is done in the various states, but we have done a lot of that here in North Dakota. And what you see in the slide is that if outside conditions are too damp to dry the grain to the desired moisture content, that then we want to add supplemental heat to lower that moisture content and allow us to continue to dry. A little bit of heat, typically 3 to 5 degree temperature rise, is all that's needed. We start adding more heat than that, and unless we have some type of stirring device in that bin, we're going to end up over drying. And that ends up costing us in two ways, both with a shrink cost because we have grain at a moisture content below what is desired, plus it costs us money to add that heat. So the over drying cost can become very substantial. So when we look at adding supplemental heat to get that final moisture content low enough, we need to be very careful that we don't add more heat than is necessary. As we look at natural air drying corn, we see a similar scenario. And what I have shown in this slide is looking at the month of October, and again, these are North Dakota climatic conditions, and they would vary a little bit as you go from state to state. But we see that October conditions are optimum, are very good for natural air low temperature drying, and we're looking at about 42 days of fan time required if we use an airflow rate of 1 cubic foot of air per minute per bushel. But the later we get in the season, the cooler the air, the less moisture holding capacity, and the longer that fan has to operate. And as we look at drying during the month of November, we're looking at drying times that are going to be almost twice as long as what they were in October. And of course the reason for that is that we're looking at air temperatures now of 30 degrees rather than 50 degrees. So the moisture holding capacity of that air is greatly limited at those colder temperatures. The tendency is, again, to add supplemental heat, and we can warm that air back up. Let's take and look at this bottom row here, November plus 10 degrees. So we're taking outside conditions and adding 10 degrees of heat. That increases the temperature to 37 degrees here in North Dakota on average, looking at a relative humidity now of 48%. And so we end up over drying the corn. Rather than being at somewhere in that 14-15% moisture range, we're down to 12.5%. Same problem that we had with wheat. And we're still looking at about 50 days of allowable of drying time required. And so what we see is that we could run the fan the whole month of November, add supplemental heat, and still only be about half done. And that's really what I'm showing in the rest of the slide, is that we end up needing to run the fan the whole month of November, the whole month of December to accomplish drying. And that becomes extremely inefficient. And so from both the effectiveness of drying and an energy efficiency standpoint, I really recommend that farmers turn the fans off once we get outdoor temperatures that are averaging near freezing. The moisture holding capacity is just too limited at that point to be efficient and effective. And then we'll hold it and finish that drying in the spring. And spring air drying, again, is very energy efficient. It works very well, and we can hold that corn at 20-21% moisture over winter. Turn the fans on. Normally in the spring, I talk about starting when outside temperatures are about 40 degrees, and then doing the drying in April and May. And again, these would be North Dakota climatic conditions, and if you're further south, you would need to adjust the time when you start the fan, but you're still using the 40-degree criteria to determine when to start that fan operation. The type of fan is also going to be very important for energy efficiency related to grain drying. And what I have done in this example is to look at a bin of corn that is 21 feet in diameter, 20-foot depth, and we're looking at a 10-horsepower fan. And in this case, we have 4 different types of fans that are used for air drying or moving air through grain drying. We had an axial flow fan that would move 5,907 CFM, which gives us an airflow rate of 1.07. The inline centrifugal fan would be this fan over here that has a centrifugal impeller, a bell-shaped inlet that brings the air in, and that fan on this bin of corn is at 0.98 CFM, or cubic feet of air per minute per bushel. The low-speed centrifugal fan will be the one here in the upper right corner. That's a centrifugal impeller operating at 1750 RPM, and that would provide us an airflow rate then of 1.4 CFM per bushel. The high-speed centrifugal fan would be similar to the one in the bottom right corner here. That operates at 3,500 RPM, and again would be at roughly 1 CFM per bushel. And so as I'm helping farmers select fans, generally what we're finding is that low-speed centrifugal fan is going to move the most airflow per horsepower through corn, and so therefore it becomes the most energy efficient. If you look back through the literature, over the years, we've typically talked about using axial fans or propeller fans, as shown here in the upper left corner, as being an energy efficient application for corn. But that requires that we keep the corn depth in that bin less than about 18 feet. And typically I find farmers today are not willing to do that. Most of them are wanting to go at least a depth of 20 feet, and so that changes the type of fan that is typically going to be the most energy efficient. And speaking of grain depth and airflow rates, over the years we've kind of used a rule of thumb, particularly on corn, that we need roughly 1 horsepower per 1,000 bushels. And that's probably a good starting point as a rule of thumb to determine what horsepower is required to give us the airflow. But that, as I indicated, is based on an 18-foot depth and an airflow rate of 1 CFM per bushel, and that would roughly give us our 0.8. We might be able to go to a 20-foot depth again with 1 CFM per bushel, but now it's at 1.1, so we'd actually be undersized a little bit at that point. And what we can see in this table is that very quickly depth works against us, that it's just going to a 22-foot depth increases the horsepower requirement to 1.3 horsepower per 1,000 bushels. At 24-foot depth, we're up to 1.7. So from an energy efficiency standpoint, it's very important that we keep the depth of that corn to about 20 feet as a maximum in order to efficiently dry that corn. If we look at airflow rate, we see the same thing. If we go with that 20-foot depth, 1 CFM per bushel, we're looking at 1.1 CFM or horsepower to do 1,000 bushels. Going just to 1.25 CFM per bushel increases that horsepower requirement to 1.8. Huge increase. And airflow is what does the drying for us. So as we try to increase the moisture content of the corn, we need to increase the airflow rate. 1 CFM per bushel will allow us to handle roughly that 20-21% moisture. To get up to about 22% moisture, we need to go up to typically 1.25 CFM per bushel. And that'll vary a little bit across the region, but that's pretty typical of what's going to be required. And so what this is really telling us is from a natural air drying standpoint, we're going to be limited in airflow to about that 1 or a little more than 1 CFM per bushel. And we're going to be limited in the initial moisture content that we can use, and that would be to about that 21% moisture range. What is shown in the bottom portion of the slide is that as corn moved in a big way in North Dakota, we had a lot of farmers that were putting up large bins. They were probably 42-foot diameter bins there for a while. Typically had about a 36-foot sidewall. And originally the idea was that they were going to try to air dry in those bins. And so if we were going to air dry, we would need an airflow rate of 1 cubic foot per minute per bushel. And to move that amount of airflow would require a 180 horsepower fan and require an operating static pressure of about 17 inches. So two things work against us. First off, there are no fans there that are typically available that can handle 17 inches of resistance to airflow through that corn. And then the horsepower requirement is far beyond what is economical. And so these big bins are great for storage, and we can put a small aeration fan on there. A 3 to 5 horsepower fan would be greatly adequate to handle the controlling the grain temperature for storage management. But if we're going to try to put wet grain in these bins and dry them, then we really need to be keeping that depth down to about 20 feet. Kind of the next step that farmers frequently look at is going with a stirring batch bin dryer. Here we're looking at a batch that might be 6 to 9 foot in depth. We have our stirring devices in there, our stirring machines as shown on the slide. Typically we'll run with an airflow rate of somewhere in that 8 to 15 CFM per bushel. And to get the most energy efficient drying from these types of dryers, we need to limit that depth to roughly that 6 to 9 foot of depth. And then we need to use the maximum temperature that we can without damaging the corn. And typically that's going to be somewhere up to about 160 degrees Fahrenheit. And so generally the bin will be designed to operate in this manner, but frequently what you'll find is that they may use a depth greater than that 6 to 9 feet, and we can fill that bin 18 feet deep and still dry in this bin, but we're going to lose some of the energy efficiency and the drying speed when we do that. Probably another common type of in-bin high-temperature dryer that we'll see is what I refer to as a continuous flow bin dryer. Probably the most common one marketed in this area is a brand called Shivers, and this is a graphic from their literature. And the process to get the most energy efficiency is going to be the same. We want to use the maximum air temperature that we can without damaging the grain. We need to limit the depth in order to keep the capacity up and the energy efficiency there. But in this case, we sweep the grain off the bottom of the bin once it's dry. It's augured up and out of this bin and into this other bin where it is cooled. From a drying efficiency standpoint, it's very similar to the bin dryer that we looked at previously. Okay, now we'll take and look at some of the cross-flow grain dryers. And this is a schematic that has been around for years of a cross-flow dryer where we have the heated air coming into the center plenum area, moving laterally through the grain and exhausting then to the outdoors. And this kind of traditional cross-flow dryer typically will have an energy requirement somewhere in the neighborhoods of 2,500 BTUs of heat required to remove a pound of water from corn. And as you're hearing people talk about, well, this improves energy efficiency by 10% or this increases efficiency by 20%, generally what we're doing is referring back to a comparison to this 2,500 BTUs that we're getting with this traditional cross-flow dryer. One of the key things that farmers can do once they've purchased a dryer to improve the energy efficiency is to dry the corn at the highest temperature that they can where we don't damage the corn. And this is research that was done many years ago. What we've got here in curved lines are airflow rates in CFM per bushel. So here we have 10 CFM per bushel on the bottom, 30, 50, 75, and 100. So that in-bin dryer that we looked at first was at roughly in that 10 CFM per bushel range. Many of the high temperature dryers are going to be operating in the 70 to 90 CFM per bushel range. So we're going to be very similar to this curve when we start looking at energy efficiency. And what we can see is that it is very important when we look at total energy required to dry is that we operate at the maximum temperature that we can. And most of the dryers today will show somewhere in the neighborhoods of 220 to 240 degree as their recommended plenum temperature. So we'd be operating somewhere in this neighborhood here, roughly again that 2,500 BTUs required to take out a pound of water. And now we're going to walk through kind of some of the different types of high temperature dryers and talk about some of the energy efficiency features or characteristics of each one. Probably the simplest dryer is a heat and cool batch dryer where we move the air through the heater, goes into the plenum, through the grain, we complete the drying, and then we just shut the heat off and cool in that dryer. Pretty much what we saw in that schematic earlier of a cross-flow dryer. One of the real challenges with this dryer is that the corn on the inside of the column here will end up being much hotter than corn on the outside, not as energy efficient, or probably will give us the most potential for problems with corn quality. The next option would be a pressure heat, pressure cool, continuous flow dryer. Same concept as we just looked at, but now we have the floor in the dryer that allows us to continuously dry in the upper portion, cool in the lower portion. One of the things that has been utilized a lot recently is to try to increase the capacity of our existing dryers. And frequently what they have done is to go to a full heat continuous flow dryer. And as indicated here in that first bullet, it's going to give us the best capacity in bushels per hour for dryer size and cost. And so we see a lot of dryers being sold this way and marketed, indicating their capacity, taking off 5 points of moisture removal, using full heat, and then in-bin cooling. And what we do here then is we dump the corn hot out of this high temperature dryer at maybe 120, 130 degree kernel temperatures. It goes into a separate bin, and there the heat that is within that grain will continue to drive the moisture from the inside of the kernel to the outside. So we do the cooling now in a bin, and so we need a bin set up with a full aeration floor, and then we deal with some of the moisture issues in that bin, and we'll talk about that a little bit more towards the end of the presentation. This has greatly improved not only the speed of the dryer, but helped us with the energy efficiency, because when we drop the corn in at, let's say, 130 degree temperature into the cooling bin and then do the cooling slowly in that bin, we're going to see probably a couple points of moisture removal in that cooling process. And so when they design the dryer, they're expecting out that we're drying, let's say, from 20% down to 17 or 17.5% moisture, and assuming then that the rest of that moisture is coming out in the cooling process in the bin. By doing this cooling slower in that bin, not only do we gain in energy efficiency, but many of the stress cracks that are associated with high temperature drying of corn occur during the rapid cooling, and so we minimize that. And so this has really been promoted as a way to get the most capacity and improved energy efficiency in a high temperature drying system. Probably we'll see numbers routinely talking of 20-25% improvement in energy efficiency. There's another little variation of that where we go with a 2 heat zone. We go with a higher temperature in the top, a little lower temperature in the bottom. This gives us a little better quality because as the corn is getting closer to dry, we're not exposing it to as much heat. The wetter corn on the top, we get a little more evaporative cooling. And so this type of dryer is being used, but probably not as much as the full heat dryer. Probably one of the things that the farmers look at as the next step is what we'll call pressure heat and suction cool. Here, the upper portion is at full heat, and we're pushing that heat through the dryer. But then rather than doing the cooling in the bin, what we're doing is pulling the cooling air in through the lower portion of this dryer. So the cooling air is coming here from the outside, going through the cooling portion, picks up the heat off of that corn, comes back, and is cycled again through the dryer and the burner and back into the corn. By doing that, we're seeing probably close to a 20-25% improvement in energy efficiency. This has been used extensively recently as a major way to improve energy efficiency. And the reason a person might look at this over doing it in a in-bin cooling, as we talked about with a full heat dryer, is that with a full heat dryer and dumping that hot corn, we'll deal with a lot of condensation and moisture issues. This concept then of doing suction cool, we're dumping almost cool corn into that bin, and we don't have to deal with those major moisture issues. So again, we're looking at roughly that 20-25% improvement in energy efficiency, and we're seeing a lot more interest in this pressure heat suction cool option. You see that concept be used with different terminology, but generally it's some type of vacuum cooling. It's being used extensively in tower dryers, as shown on the right here, where we are pulling the air in again through the lower portion that goes through the fan and burner and up into the upper portion of the tower. It can be done in a traditional horizontal dryer as well, where again we're pulling the air through, it comes into the fan and into the heated plenum area. So again, being used in a variety of dryers. I'd say 20-25%. Some people have indicated that they've measured as much as a 30% improvement in energy efficiency. And particularly when we're looking at drying in the cooler portion of the year, I think that there's a huge gain that can come by using some type of vacuum cooling or heat reclaim on that cooling portion of the dryer. Now this one would be kind of the next step beyond that vacuum cooling, where we're going with pressure heat. So we're heating again that upper portion of the dryer. We're doing a suction cool or vacuum cool, where we're pulling the cool air in and picking that heat up off the cooling portion of the dryer. But we're also putting some housing along the outside of the dryer, and so we're doing a heat reclaim here on the lower, maybe typically about 20% or 15% of that drying column. This air coming through the final portion has less moisture in it because we're working with corn that is almost dry, and this is by far going to give us the best energy efficiency. So we're kind of getting the best of everything with this design from an energy efficiency standpoint. Now, just to try to put these numbers in perspective, or the different types of dryers in perspective, this is what one dryer company lists. And so it's not based on research. I'm not aware that we've got good research data that really gives us these numbers for today's dryers. But this is looking at the various dryer options they have, and then what they look at as the drying cost to take out 5 points of moisture. So with the pressure heat, pressure cool, which would be the kind of the basic continuous flow dryer, we're looking at about 16 cents to do the drying. If we go to the full heat, we're looking at about 13 cents. We go to the pressure heat, vacuum cool, we're down to about 12.5. So very little difference, as I indicated earlier, between that full heat and the pressure heat, vacuum cool. And then what we've got, the best option then from an energy efficiency was the last one, where we're doing the pressure heat, vacuum cool, plus the heat reclaim. I'm getting a lot of noise coming into my ear.
Yeah, can everybody make sure that they have their phone muted, please?
Sound like somebody was out listening by the dryer. Okay. Some of the other improvements that have been done to grain dryers that are helping us from an energy efficiency and grain quality standpoint is a stage temperature dryer. As shown on the left, we already talked about that briefly with the two different temperatures in a dryer. Here, where we can run the higher temperature on the upper portion, back off the temperature on the lower portion, we're getting more evaporative cooling on the top, and that then allows us to go with a higher temperature without affecting the grain quality, which then improves our energy efficiency. Another option that is being used is a grain turner or grain inverter, where if we look at this diagram here, the corn coming down the dryer at partway down that column is physically moved from the inside to the outside, and vice versa. It moves from the outside to the inside. And that then helps us from a grain quality standpoint, because we don't have the corn exposed to the high temperatures for that entire drying cycle. And then that also gives us the ability to use a little higher temperature without damaging the grain, because that we don't have that dry corn next to the inside. So it's a way to improve both grain quality and energy efficiency. There's other concepts that are being used to accomplish that same type of thing. Here we're looking at what I refer to as a differential grain speed dryer, where we have the metering rolls here in the bottom. We've got two of them rather than one. The metering roll on the inside, near the inside of the column, is moving the corn much more quickly than on the outside, and that then creates, again, a more uniform drying and both a grain quality improvement as well as energy efficiency improvement. Another company has gone with what they call a moisture equalizer, which is this little diverter that is in the grain column. Again, allows the grain near the inside of the column to move more rapidly than grain on the outside of the column. Their testing would indicate that they're seeing a 1 to 4 pound increase in test weight versus this old style of where we don't have any variation in grain movement within that column versus some type of a moisture equalizer. That allows them then to dry at a higher temperature, which improves the energy efficiency and capacity of that dryer. Another option that is being used is to vary the thickness of the grain column. Here in the initial portion of the drying process where we're working with high moisture corn, we'll go with a narrower column thickness that allows the air to become saturated and move through more quickly in that portion of the dryer. As we get to the heating portion or the cooling portion, then we're looking at a wider thickness, and that again is accomplishing some of the same kinds of things where we're making the most energy efficient use of that air, getting the most drying capacity out of that air. As I indicated earlier with natural air drying, even with high temperature drying, the proper fan selection is important. And it'll depend on what type of grain that we're drying in the dryer. This is, again, literature from one specific company showing why they have gone to a centrifugal fan. The curve here on the top shows that it gives them the ability to have a wider operating range. So that dryer then is able to handle corn, wheat, and other crops where if you have a dryer that is designed specifically for corn, it might be targeting in on a much narrower operating range and have a different type of fan used than if we were going over a wider range. So as we look at selecting a grain dryer, we need to know the type of grain that's going to be dried, what's the flexibility of that dryer as part of selecting our dryer. Another dryer design is called the mixed flow dryer. Rather than the cross flow as we have seen previously, the mixed flow dryer has these air channels that the air comes from the inside to the outside through them. And as shown here in kind of this graphic, we have hot air coming out through this channel, and then it will seek an outlet, and it will either go up or down to these openings that we're able to see on the exterior of the dryer. And so some of the air is moving up, some of the air is moving down, and that's kind of where we get the mixed flow concept. But because the grain is constantly moving through the dryer and we have the exposure to the high temperatures varying throughout that drying process, again, that allows us to go with a higher operating temperature than what we might in a traditional cross-flow dryer. The other thing, though, that is different about this dryer design is, I indicated earlier, most of the cross-flow dryers will be operating in the range of 70 to 90 CFM per bushel as an airflow rate. The airflow rate in this mixed flow dryer is typically in the 40 to 45 CFM per bushel range. So if we think back to that graphic, if we go with a lower airflow rate, that gives the air more time to pick up moisture, and we tend to be more energy efficient. And so this design of dryer has been promoted as being very energy efficient and producing good quality grain, and that's true. Again, if we make a comparison to that traditional cross-flow dryer, this dryer probably will see an improvement in energy efficiency of 20, 25, and even 30%, depending on the comparison. However, when somebody calls and asks me which dryer is the most energy efficient, there is not one that is particularly more efficient than the others. If you compare this design, the mixed flow dryer, with a cross-flow dryer that incorporates all of those energy efficiency features. So we're doing the heat reclaim, we're doing the vacuum cooling options. That dryer design can be very comparable in energy efficiency to the mixed flow dryer. So you can't just say, well, is it cross-flow or is it mixed flow, and one is more energy efficient than the other. You really do need to look at the specific design. As we would already saw with natural air drying, as the temperatures got cooler outside, the moisture holding capacity was less and we became more energy inefficient. If we're looking at a high temperature dryer, the same thing is going to be true. And what I'm showing here is comparing outside air temperatures ranging from 40 degrees above to minus 20 degrees Fahrenheit. And then looking at the amount of energy that is required to heat that air as it goes through the dryer. And as you would expect, the energy cost increases as it gets colder. And so that's another part of making that management decision as to what is going to be the most energy efficient. We need to look at, what the dry down potential is in the fall in the field, compare that to the potential for harvest losses, but we also then need to also look at what drying at colder temperatures will do to our energy efficiency. And so typically I think the consensus is that we're better off starting drying a little bit earlier than what people might have a tendency to do so that we can make use of the warmer temperatures for our air drying. As I'm getting calls and have looked at grain dryers, I've done grain dryer energy audits on roughly 50 grain dryers. And as I interact in my extension role helping farmers wade through the information as they're selecting a dryer, you will find different numbers listed as far as the energy efficiency of a dryer. I have had one company that claimed that they were able to dry with an energy efficiency of about 1,000 or 1,100 BTUs of heat to take out a pound of water. And what I have shown here is a table out of a textbook that looks at the heat of vaporization. And if we look at doing it, let's say, when it's 32 degrees outside, and if we're going to do corn at 20% moisture, we're looking at roughly 1,200 BTUs to take out a pound of water. The heat required to vaporize a pound of water at 40 degrees is roughly 1,100 BTUs. So that's kind of what I would call the 100% energy efficient, is this 1,200 BTUs to take out a pound of water. None of our dryers are typically going to be able to operate at that level of energy efficiency. And so I say realistically, probably a minimum of about 1,500 BTUs to take out a pound of water is kind of the threshold of practical efficiency today. And there are a number of dryers out there that are claiming that they're in that, approaching that range, in the 16, 17, 1,800 BTUs to take out a pound of water. From my experience in looking at actual on-farm applications, I'd say we're probably more realistic in the 1,800 to 2,000 BTUs to take out a pound of water. I want to just touch briefly on dry aeration and in-storage cooling. Both of them were designed years ago to improve corn quality and to improve energy efficiency. But I think that it's been some time since we've really looked at these in detail, and there's some details there that I think are very important. Dry aeration is the process where we take the corn hot out of a high temperature dryer, we put it into a dry aeration bin and allow that corn then to sit there for 4 to 6 hours without being cooled. So we're dumping corn at, again, maybe 130 degree kernel temperature into this bin, let it sit for 4 to 6 hours. That moves the moisture from the inside of the kernel to the outside of the kernel. And then when we do the cooling, we'll roughly see 1/4 of a point of moisture removal for every 10 degrees that we cool. So we're seeing probably in the neighborhoods of 2.5 points of moisture removal. This will improve the dryer capacity by 50 to 70% and reduce the energy consumption by 15 to 30%. So these are big benefits for doing dry aeration. The downside that sometimes farmers are forgetting about is that during that tempering period and during the cooling period in this bin, we're seeing tremendous amounts of condensation. And so it's very important then that we move the corn from this bin to another bin, so we mix the corn that is along the wall that has gotten wet and mix that with the dry corn for storage. But it's imperative that we do that moving of the corn to another bin. The other option is in-storage cooling. Again, we're dumping hot into this bin. However, now we immediately cool that corn down. And we probably won't see as much of a moisture reduction because that corn isn't sitting there going through that full tempering cycle. But by doing the immediate cooling, we are reducing the amount of condensation that is occurring. And the idea was we can then leave the corn sit in this bin and not have to move it to a separate storage bin. However, if you read through the literature, you see that it was not recommended when outside temperatures are below 50 degrees. And we've got a lot of our drying and storing of corn being done at temperatures that are cooler than 50 degrees. And so we're ending up with a lot of condensation on these bin walls that are causing us storage problems. Now, some of the farmers have gone to partial cooling where they'll cool the corn maybe to 90 degrees in that high temperature dryer, dump it into the bin and finish the cooling, and that will reduce the amount of storage problems. But it's critical that we keep in mind the importance of minimizing condensation if we're going to leave it in that bin. The last thing that I'm going to quickly touch on today is to just quickly go over some of the information on doing a grain dryer energy audit. That is being offered more and more for a number of reasons, including has been used to apply for energy grants. What we look at with a grain dryer energy audit is to look at the existing energy use, make a prediction of what the new system will use as far as energy, calculate what the savings will be, and then come up with a simple payback. If we look at an example that I pulled from one of my audits, in this case the farmer was drying 239,592 bushels of corn. Average moisture content was going in at 23.69. The average final moisture was 14.72. We calculate out the pounds of water removed per bushel, and that was 6.52. And I've shown how we calculate it. And it's not just a normal shrink calculation. You need a little more of a process to get an accurate estimate of what the pounds of water removed will be. We look at the amount of fuel consumed, in this case roughly 46,000 gallons of propane, and can calculate then what the energy use was per pound of water removed. And in this case it was 2,692 BTUs per pound of water removed. And I'm frequently seeing on-farm numbers that are very similar to this, probably ranging from about 2,500 to 3,500 BTUs to take out a pound of water. Now, when you're purchasing a dryer, you can request that the company run a energy simulation, and I'll show you two. And this is what they will come back. This is for a specific dryer. It lists the different energy costs, how that dryer is operating, goes through all of their estimates, and comes up then with an estimate on energy used per pound of water removed. And we won't look at it on this one. We'll look at it on this one just as an example. Different company, same kind of numbers, but it's important to look at what they're listing as far as original moisture, final moisture, what the ambient relative humidity is. This one was run assuming 50% relative humidity, and you need to determine whether that is realistic for your environment or not. I'd say probably 60% would be more realistic. Ambient outdoor temperature, 50 degrees. Again, they're operating at 240 degrees. They list the fuel cost, the total cost, and then the efficiency at 1,497 BTUs to take out a pound of water. And so, again, like I said, this is kind of the upper limit of what some of them are showing. Realistically, I tell farmers it'll probably be closer to that 1,800 to 2,000, but they're indicating a pretty energy efficient dryer. So a very, very quick run through on energy efficiency in grain drying systems. As most everybody has a website, this is a way to find information that I have available. So I pretty well used up my hour of time frame, but we may have time for a couple questions if there are questions.
Anybody have any questions? You can either unmute or you can use the Q&A and type them in. Maybe we got some already. Hang on a minute. Get them so I can see them here. Come on. Brian Holmes, can bin liners solve the problem of condensation?
The bin liners can help, and again, that was a concept that was used in the 70s and 80s, where you would put in either an entire internal bin wall, or many of them would put in just channels along the wall. And the more airflow that we can move along that exterior wall, that's certainly going to help us to reduce the amount of condensation that occurs. My reading of the material was that it helped, but did not eliminate the problem. The other thing that people are doing to try to minimize the amount of condensation off the bin roof is to put in a fan in the bin roof so that we suck the air out of that headspace on top of the grain, and that too will help reduce the amount of condensation.
All right. Thomas asked about getting a copy of them. I think it's the presentation, which we can do. We can get that to you. Actually, if you just want a handout, if you go to the upper right-hand corner, you'll see the word feedback. And if you move over 2 things to the left, you'll see a group of pages, and the handout for today's presentation is there. Tom, if you want the actual PowerPoint, we can supply that to you. Just send me an email, and I'll return that by email. Any other questions? Well, I'm not seeing any at the moment. Ken, is there anybody that's actively doing independent testing of grain dryers?
No, not that I'm aware of. Years back, probably again in the 70s and early 80s, there was a Canadian group called the Ag Machinery Institute, and they would do some dryer tests. But they're the only ones that I know of that have done any testing, and PAMI quit doing that in the early 80s. So at this point, I'm not aware of anybody that is doing any testing of the dryers.
Okay. And Purdue has a tool up, correct, for doing estimates on some types of dryers?
Yeah, and unfortunately, I think that there are some bugs in the system that is on that web one. I was going to use it the other day and was getting numbers that were not reasonable, and I had a opportunity to visit with Sam McNeil at Kentucky, and he too had used it and come up with information that wasn't accurate. And so we both relayed that to Purdue, and hopefully they will make modifications. But at this point, I think there's a bug in the program somewhere.
Okay. All right. Well, if we have no other questions, we'll call it a day. If you do think of something, you can email Ken or myself, and if you email me, I'll get the questions to Ken. Otherwise, we're going to send out a post-evaluation here later on this afternoon. For that, I thank you, Ken, for taking your time, and hopefully your feet will dry out soon.
You're welcome, and things are looking better.
Okay. Thank you.